Hello everybody, welcome back to my channel. Today we're going to talk about blending problems or mixing problems, right? And the idea is, I think there are essentially two kinds of blending or mixing problems, and I want to explain to you what the main difference is and what that means in terms of selecting the type of a model or variables you're going to need to use in this case. So you have a blending or mixing problem essentially if you are taking some inputs and combining them, putting them together to create one or more outputs. So I usually like to explain this with a picture. So let's say I have some raw materials. I have these buckets with things in them, right? This could be liquids or something solid. Let me call this material 1, 2, and 3. And I want to use these or mix them together to make some final products, right? Let's say I also am making 3 final products. Let me call them A, B, and C. So the idea is I can take some of this and throw it here and or here. Likewise, I could take the second raw material and use some of it to make the products. It doesn't have to be that all materials go into all products, but it's possible. And I also have a choice to use the third material. Oops, not twice in the same place. Third material to make the products. Great. So typically the question in these problems involves the following. Excuse me. You have some limited amount of these materials, right? You may have some required production amount for the products. And there could be a recipe involved. That is to say, you have some rules, okay, to make product A, you need the following things to happen so that product A is of sufficient quality, right? And I'm going to call this the recipe. Let me write that here. There's going to be some sort of recipe rules. All right? And there could be, costs associated with the raw materials and revenues associated with the products, and you might be, for example, maximizing profit. Now let me go back to the question of the recipe, right? I like to divide these problems into two kinds of recipes. What I'm going to call the fixed recipe and the flexible recipe. The fixed recipe is basically what you get when let's say you're making a cake, right? You're going to say, all right, for every pound of this product, let's say product A, you're going to need, so many ounces of material 1, so many ounces of material 2, and so forth. So that is to say, if I tell you how much product A I made, you can tell me exactly how much of each of the raw materials you used, because the recipe is fixed, right? The other variation is when the recipe is flexible. I'm not going to tell you exactly how much of each material goes into each unit of the product you're making. The only requirement I have is as long as the final product satisfies some characteristics, I don't care how much you mix in of each of the materials. Let me give you an example. Let's say I am making orange juice, right? Let's say Minute Maid. Coca-Cola is making Minute Maid, and they do it by squeezing some oranges. But there are many kinds of oranges that you can be using. Each of them has a different flavor and acidity. Let's consider the pH of the orange juice. But Minute Maid, because of its characteristic flavor, needs to have a certain acidity, let's say, right? A pH of a certain value. When I'm mixing in my oranges, some of them have a higher pH or a lower pH, but the recipe could be like this. As long as the resulting pH of the final mixture of orange juices is equal to a given number, I don't care how much you mix of each orange. So notice, in that case, if I tell you, oh, I made 10 gallons of Minute Maid, you're not sure how much of each orange you squeezed in there, because the only requirement was as long as these 10 gallons have a certain pH, you're fine. So that is what I'm calling the flexible recipe. I am only given some rules for the final product, but knowing how much you made of the product does not allow you to tell how much you used of each individual ingredient. Okay? So in what way do these kinds of recipes affect the mathematical model? In the following way. If your recipe is fixed, I only need one variable per final product. Why? Because if I tell you how much A you made, you can tell me how much of components or raw materials 1, 2, 3 you used. If the recipe is flexible, to be able to do all the calculations I need in the mathematical model, I have to know exactly, let's say you made product A, I'm going to divide this by mixing some material 1, some quantity of material 3, and some quantity of material 2. I'm going to need to know exactly how much of each of those you put in there. So in a flexible recipe situation, I'm going to need one variable per pair raw material comma final product. Okay, this is the pair in parentheses. So let's say in this case I can mix any of the 3 raw materials to make any of the 3 products. There is a total of 9 combinations. How much 1, 2, 3 did you use to make A? That's 3 variables. How much 1, 2, 3 did you use to make B? That's another 3 variables. In total, you have 9. If this problem had a fixed recipe for ABC, I would only need 3 variables, XA, XB, and XC. That is to say, how much of each of the products you made. Okay? In this video, we're going to focus on the flexible version of the problem. If you were interested in the fixed version and you by accident landed here, I'm going to put a link up top that you can click on to be directed to the video that treats the fixed version of the problem. All right, so here's an example of a problem with the flexible recipe. Don't worry about the spreadsheet for now, just focus on this explanation here and then we'll go there in a minute. This is in the context of mixing petroleum components to make gasoline. Noble Oil blends 3 petroleum components to produce 3 types of gasoline. So we have 3 raw materials and 3 final products, as in my introductory picture that you saw a while back. So the 3 products are called regular, super, and power gasoline, and let's call the 3 raw materials component 1, 2, 3. Each gasoline is characterized by a minimum octane rating, so that's the quality requirement of the product. And this first table tells you what is the minimum octane rating required for each gasoline, how much they sell for per gallon, and a minimum production requirement. The second table gives you data about the raw materials or components. They have their own octane rating, they have a cost, and an availability. So this is kind of like that pH example that I mentioned to you earlier. The components you're mixing together have their own individual octane rating. As long as the final mixture, which is the gasoline, attains the given octane rating, we are good. That's why the recipe is flexible. I don't tell you exactly how much component 1, 2, 3 to mix together to make, for example, super gasoline. Great. That means we know we're going to need 9 variables because we can mix any of the 3 components into any of the 3 gasolines, right? And so let's take a look at quickly at a math model here for this. So I'm going to make a variable Cij, right? How many gallons of component I, which could be 1, 2, 3, are used to make gasoline J, which could be RSP. So I'm going to have a variable C1R, C1S, C1P. How much component 1 went into R and S and P. Likewise, we have C2RSP, C3R, 3S, 3P. Those are my 9 variables. So this problem asks you to maximize profit. It didn't say that here, I'm just telling you. So it's going to be revenue minus cost. Every gallon of regular gasoline made sells for $4.4. So I take $4.4 times what? Well, how many gallons of regular did you make? Well, because I make regular by putting together components 1, 2, 3, the total amount of regular I make is inside this parenthesis. That is, how much component 1 was used for R, how much component 2 was used for R, how much component 3 was used for R. Summing these three things gives you the total production of R gasoline. Similarly, I have production of super and power. That's the revenue part minus cost. Well, it costs me every time I use component 1. So $3.1 times all the gallons of component 1 that were used. And that is, I use 1 to make R, plus I use 1 to make S, plus I use 1 to make P. So I'm summing all C variables that have a 1 in them, right? That's the usage of component 1. Minus the cost of component 2, usage of component 2, and the cost of component 3 times usage of component 3. Great. Now, the two easy requirements are make enough gasoline and don't use more component than what you have. The first three constraints are make enough gasoline. The production of R is in this parenthesis here. I copy and paste that down here. Production of R at least 20,000. Production of S, copy down here, at least 20,000. Production of power gasoline, at least 20,000. The usage of the three components is already here in the objective. Take those three expressions in parentheses, copy them down here. Usage of component 1 at the most, what you have of it. Usage of 2 at the most, what you have. Same for 3. The last thing you have to do is the quality constraint or the octane rating constraint. And that's going to be a weighted average, right? When you throw in component 1 into the R mixture, every of those gallons comes in with its octane rating, like its weight. So I throw in this many gallons of component 1 into gasoline R. They come in with this weight, 83 octane per gallon. Plus the gallons of component 2 I threw into R. Each of them has their 90 octane per gallon. And for component 3. If I take this expression here and I divide by the total production of R gasoline, I'm going to have its weighted average octane rating per gallon, which needs to be 87. But if I were to divide this by a bunch of variables, I would get a nonlinear formula, which we don't want to use unless it's strictly necessary, because we're dealing with linear programming. But I could simply multiply both sides of this inequality by the denominator, which was the production of regular. So that denominator disappears from the left-hand side and appears on the right-hand side, multiplying the 87. So this is just a linearization of a weighted average calculation. And we do the same for the other two. Okay, so when we go to the Excel, I'm going to call this constraint the linearized octane rating, just so you remember what that is. Great, let's go to the Excel now. We're going to take all of this and make it work. Remember, we have 9 variables, right? 1 per pair component gasoline. Let's go here. So here we are. I made this rectangle, right? Whenever you have variables with 2 indices, they refer to 2 entities in your problem, it is often beneficial to have a layout for the variables that is a rectangle with as many rows as there are values for the first index. The I index could be 1, 2, 3, in as many columns as there are values for the second index of that variable, the J index, RSP. So if I pick a cell in this gray block, you can tell me which C variable that is. This one is C2P. How much component 2 goes into power gasoline, because it's in the row of 2 in the column of P. Great. So let's deal first with the easy things, right? The usage of each component has to be at most its availability. But because I have this rectangle of variables, the usage of component 1 is the sum of all C's that have a 1 index, right? 1R, 1S, 1P. These are the guys in this line here. So if I just sum this line like that, I have the usage of component 1. And because I have the rectangle layout, I can simply copy down this formula to get the usage of the other two components. And that's making my life a little easier. Okay? Great. So this is going to allow me to implement the constraint, don't use more components than what you have. Likewise, we have an analogous version of this, which is make enough gasoline. So the production of any gasoline is the sum of all the C variables with a fixed J for that gasoline, right? So the 1R, the 2R, and the 3R give you the production of the regular gasoline. So if I sum these guys in the column here, I'm calculating exactly that. Production of regular gasoline is like this. And again, the layout is going to help me because I can copy this to the right-hand side and get the production of super and power gasolines. Let me copy that like this, right? And there you go. Now, let's go to those linearized rating formulas. Remember that, let me go back to the math here. On the left-hand side, what did I have? I had all the components that went into that gasoline multiplied by the respective octane ratings of those components, right? And that's what I wanted to put here. So the octane rating for the regular gasoline, I'm going to do, it's not just a sum because it's number times variable plus number times variable, etc. When I have that number times variable plus number times variable, I have to use a sum product because it's a sum of products. I am multiplying the ratings of the components, right? 83, 90, and 95 by the amount of each component that went in there. And this will produce for me 83 times C1R, 90 times C2R, plus 95 times C3R. If you go back to the math and take a look. Notice that because we're always trying to copy more and type less, I want to copy this formula over to make the corresponding version for super and power gasoline. When I do that, I would definitely want the block, this block here, to update to the next block and become the super variables. And then one more time for power. But this collection of three numbers in the blue box is constant across these formulas, so I don't want that to move over to an empty area. That means I have to anchor the blue part of this, right, with those dollars. Remembering to apply the dollars quickly to a range like this, if you're selecting it like I did, on Windows you press F4 or function F4 depending on your keyboard configuration, and on the Mac it's Command T. Some newer Macs with the newer Excel versions also accept the F4, I believe. Okay, so if I close this parenthesis here and hit enter, I can copy this formula forward. Oops. And do it like that. And you'll see that the blue box was fixed and I updated the variables like we wanted to. Great. On the other side, on the right-hand side of that formula, what do we have? We have the required octane rating of that particular gasoline times the total production of that gasoline. So let's go back here. The required octane rating for regular is here, right? 87. times the total production of regular we already calculated. It's here. It would also work, of course, if you just want to repeat and type sum of C1R, 2R, 3R again. That's equivalent. There's no need to dollarize anything because when we copy this over, we want both the 87 to become 89 and the production of R to become production of S. So drag that across like this, and we have it here. Great. The last pieces of this puzzle are just the objective function parts. Let's calculate it separately. Revenue, cost, and profit, right? Well, revenue, if you go back to the math real quick, it's just the production of each gasoline times the selling price. And the cost part will be the usage of each component times the corresponding component cost. So let's do that. These are going to be also some product formulas. The selling price of each gasoline, they are here. And the production of each gasoline, they are here. So that's my revenue, according to the math. The cost, the costs of each component, they are here. And the usage of the components are here, that we had already calculated, right? And profit, right, it's simply the difference. Okay, we're ready to go to Solver and solve this. Let's go there. So here we go. The objective, well, it's the profit. This guy here, B19. We're maximizing. The variables will be all our 9 variables in the gray block, so select the whole gray block. And the constraints, there are 3 groups. One group says, don't use more raw material than what you have, so the component usage in E4 through 6 is less than or equal to the component availability in G4 through 6. The next group is make enough gasoline. So the gasoline production in row 7, so B7 through D7, should be greater than or equal to the required production in row 9, so B9 through D9. And finally, we want to impose the octane rating requirement. So we have to say that the formulas in row 13, B13 through D13, are greater than or equal to the ones in row 15, B15 through C15. Then finally, just enforce that the variables are non-negative and change the solving method to the linear solver, simplex. And we're ready to solve this. Let's see. Okay, so let's see what happened. We had a revenue of $380,000, cost of $279,500 with a profit of $100,500. This is of course assuming that all the gasoline you make you'll be able to sell. Notice here we used all the components we had, all the gallons. The octane ratings, they are, because these two values are matching, right? It means we matched the requirement exactly. If you want to know the exact number, just divide both sides by the production of the gasoline to get back the original formula. And if we look here, this is not only telling us how much of each gasoline to make, but also telling you how to make it, because you have the breakdown of those gallons. So to make regular, you used all 3 raw materials. To make super, you only used the first and third materials. And to make power, you only used second and third. If it is initially a bit counterintuitive to you as to why are you making more of the gasoline that sells for the cheapest price, notice that this is a profitability problem. So it's likely the case that given the recipes that were chosen for each gasoline, regular gasoline turns out to be the most profitable, and therefore that's why you're making more of that one. Right? So when Solver is solving this problem, it is not only looking for the recipes, but is looking for the recipes in such a way that you both fulfill quality requirements, satisfy availabilities, and maximize the profitability of the recipe. So it's doing all of that at the same time. Okay, great. So I hope this was a helpful example to illustrate how to deal with the blending problem with a flexible recipe. Thank you for watching, and I'll see you guys in another video. Bye-bye.